Hello, this is Matt Dean with A Plus College Rating, and today we're going to work some practice problems that deal with the ideas of uniform circular motion and rotation. The first problem we're going to begin with, practice problem 1, deals with the idea of torque. So it says a uniform board of mass 30 kilograms and length 3 meters is used to make a seesaw. A buoy of 52 kilograms sits at one end of the seesaw. How far from the buoy side of the board should the fulcrum be placed in order to balance the seesaw? No other masses will be used. So let's draw out what we have first. So we have a board, uniform board. We have a buoy, we'll just use a B, sitting on one side. We're going to draw in the center of mass of the board. Since it's uniform, all that mass is uniformly distributed. It's distributed evenly throughout the length of the board. We're going to think of the center of mass as the point at which all of the mass, all of the weight of that board is located. So the buoy is 52 kilograms. He's on the left. We've got to put a fulcrum somewhere in between the buoy and the center of mass to balance out the seesaw. The idea here is that the torque on the left, the buoy side, has to be balanced out by the torque on the other side, on the right. If those torques are equal and opposite, the seesaw will be in rotational equilibrium. It'll balance out. So you guys hopefully know that torque is equal to force times the length of the lever arm. And if the force is applied at some 90-degree angle, we also want to add in sine of theta. In this case, we're applying a force at a 90-degree angle to the board, so we're going to not worry about the sine of 90 because it's 1. So the buoy's torque is going to be force times length of lever arm, and that's going to be equal to the torque caused by the weight of the board, force times length of lever arm. So let's put in what we know about these forces down at the bottom. So the force on the buoy side will be his weight. So we're going to take his mass. We're going to multiply that by the acceleration due to gravity to turn it to weight. We're going to multiply that by the length of the lever arm, which is the distance between that force and the axis of rotation, the fulcrum in this case. We're going to call that distance x. So times x, because we don't know that distance right now. And that's got to be equal to the torque caused by the weight of the board. Well, the board has a mass of 30 kilograms. So we're going to convert that to weight by multiplying by acceleration due to gravity. Now here's the tricky part. Remember that the whole board is 3 meters in length, which means the distance from the center of mass to this end is 1.5 meters. So if this distance between the buoy and the fulcrum is x, then the distance between the fulcrum and the center of mass has to be equal to 1.5 minus x. So we're going to call the distance, the lever arm distance between the fulcrum and the center of mass, 1.5 meters minus x. All right, now we just do the algebra. We solve that out for x, and once we do, we get x equals 0.918 meters. So that's the distance between the buoy and the fulcrum. And again, we called that distance x. All right, so that's practice problem 1. Now let's move on to practice problem 2. Practice problem 2 looks like a very similar problem. It says a uniform board of unknown mass, so this time we don't know the mass of the board, is used to make a seesaw. A buoy of mass 35 kilograms sits at one end of the seesaw. It is experimentally determined that the fulcrum must be placed 0.756 meters from the buoy in order to balance the seesaw. No other masses are used. What is the mass of the board if the board is 3 meters long? So same basic setup as we had in problem 1. We've got our buoy. There's a fulcrum in here somewhere. Here's the center of mass. So again, the torque on the buoy side has to equal the torque on the right. Again, torque is force times length of lever arm. So the force on the buoy side is going to be his mass, which we'll call 35, times g, to make it be a force, to make it be weight, times the length of his lever arm. Now it says it's experimentally determined that the fulcrum must be placed 0.756 meters from the buoy. So that distance is going to be 0.756 meters. Well, that has to equal the torque caused by the weight of the board. We don't know the mass of the board. That's what we're trying to find. So we're going to say mass. we've got to multiply that mass by g to turn it into a force. And now we've got to figure out the length of the lever arm on this side. Well, if the whole board is 3 meters long, the distance from the center of mass to this side is 1.5. We already know that from the buoy to the fulcrum, that is 0.756, which means the distance from the fulcrum to the center of mass has to be 1.5 minus 0.756, which gives us 0.744 meters. So this distance is 0.744 meters. All right, we only have one variable, so we do the algebra. We solve this equation out for mass, and when we do, we find out that the mass of the board is 35.6 kilograms. All right, so that's practice problem 2. Now let's move on to practice problem 3. Practice problem 3 deals with a slightly different topic. All right, here's practice problem 3. What is the maximum speed at which a car can safely travel around a curve if the radius of the curve is 100 meters and the coefficient of friction between the tires and the road is 0.20? All right, so we're assuming in this problem that you got the car going around the curve, and what we have to realize here is that the frictional force between the tires and the road is providing the centripetal force that keeps the car going around the curve. So we're going to take the frictional force and we're going to set it equal to the centripetal force. Now I'm hoping that you guys remember, and we're assuming here that the car is on flat ground. We're going to say that the frictional force is equal to mu, the coefficient of friction, times the normal force. And we know that centripetal force is mv squared over r. Well, since we're on flat ground, the normal force is equal but opposite to the weight. So we're going to say mu, we're going to put in mg for weight or normal force. That's equal to mv squared over r. Notice that the masses cancel out. We're trying to solve here for the velocity, so let's multiply both sides by r. Cancels over here. Take the square root of both sides, so we end up with v equals the square root of the radius times the coefficient of friction times acceleration due to gravity. So v is going to equal to the square root of 100 meters, the radius, times mu, 0.2, times g, and we'll use 10 for g. So we solve that out, take the square root, and we end up with a velocity of 14.1 meters per second. All right, let's continue on with problem 4. A man sits on the seat of a Ferris wheel. The radius of the Ferris wheel is 15 meters. The Ferris wheel spins one complete rotation in 10 seconds. The wheel moves in uniform circular motion. So the speed is constant, but it's accelerating because the direction is constantly changing. The mass of the man is 62 kilograms. What is the period of the Ferris wheel's rotation? Now remember that the period is the time it takes for one complete rotation. So the problem gives this to us. It takes 10 seconds for one complete rotation. So this is 10 seconds. Next, it wants to know the frequency. Now remember that the frequency is the number of rotations per second, and that the frequency is equal to 1 over the period. So in this case, that's 1 over 10 seconds. So 1/10 of a second, or 0.100. And remember, we're talking about cycles per second, or rotations per second in this case. That unit we call the hertz. So we'll use Hz. Next, we want to know the angular velocity. Now remember, we use this as the symbol for angular velocity. Angular velocity is equal to the change in the angular displacement over time. So let's think of it this way. Let's think of this wheel spinning around one complete time, one complete circle. The angular displacement for one complete circle is 2 pi radians. And it does that in a time of 10 seconds. So 2 pi radians over 10 seconds. We divide that out and we get an angular velocity of 0.628. And our units on that would be radians per second. Now, next we're asked to find the tangential or the linear velocity. And to find that linear velocity, all you need to do is know this formula, that the linear velocity is equal to the radius times the angular velocity. So the length of our radius here is 15 meters times our angular velocity of 0.628 radians per second. We multiply that out and we end up with a linear or tangential velocity of 9.42 meters per second. Now we're trying to find the apparent weight of the man when he's at the top of the wheel's rotation cycle. So let's pretend that this is our Ferris wheel and that right now the man is sitting up here in a seat like so. Let's just pretend that this thing is spinning this way right now. We need to think about the forces acting on the man. Remember that when something is in uniform circular motion, the centripetal force is the net force acting on that object. So the net force acting on the man is the centripetal force. It's also important to remember that the centripetal force is always pulling toward the center. Well, in this case, we have the weight acting on the man, and it's acting down toward the center. We also have a normal force acting on the man, and that's the force between the man and the seat, and it's pushing up on him. So we're going to write out a little equation for the net force. The net force acting on the man, which is the centripetal force, is equal to the weight acting in the direction of the centripetal force minus the normal force. The normal force is the support force we feel. That's what we interpret as weight. So this problem is actually asking us to find the normal force. So we want to take this equation and solve it for normal force. So let's clean it up just a bit. Let's write it out this way. If we do a little algebra on this and we solve it for n is going to be equal to the weight minus the centripetal force. Well, the weight of the guy is just going to be his mass, 62, times g, so 620, minus Fc. So you guys, I hope, remember that the centripetal force is equal to mv squared over r. So let's go ahead and calculate that centripetal force. Let's take his mass, 62 kilograms, times the v. This is the linear velocity, the tangential velocity, so 9.42. Got to square that over the radius, which is 15 meters. Solve that out for Fc, and we end up with a centripetal force of 366.8 newtons. So now we want to go back to this equation over here. So our normal force is 620 minus 366.8 newtons. So we end up with a normal force of 253 newtons when we round it off to 3 sig figs. So the guy at the top of his rotation would feel like he weighs less than he actually weighs. Feels like he weighs 253 newtons. He actually weighs 620 newtons. Now, the next problem wants to know what's going on down here at the bottom. So let's clean up a little bit of our work here. So down at the bottom, the same idea, but we have some forces acting in different directions. The idea is still that the centripetal force is the net force acting on the guy. At the bottom, though, we have weight acting down, and we have the normal force, since he's sitting in the seat, acting up. Well, that means that the centripetal force is equal to the normal force acting toward the center in the direction of the centripetal force minus the weight acting away from the center, which means that the normal force in this case, or his apparent weight, is equal to Fc plus W. When the last problem we established the centripetal force was 366.8 and that the weight was 620. So we have to add 366.8 plus 620. His apparent weight or normal force at the bottom of the rotation, therefore, is 987 newtons. All right, so let's move on to problem 5. In this problem, a 2 kilogram bucket on the end of a 1.5 meter rope is swung in a vertical circle 4 times in a 2-second period. The bucket experiences uniform circular motion. What is the period of the bucket's rotation? Again, remember the period is the time for one rotation. So let's take the total time, 2 seconds. Let's divide that by the number of rotations, 4, and that equals half a second per rotation, or we'll just say half a second. That's the time for each rotation. Well, next we're asked to find the frequency. We know that frequency is 1 over the period. So frequency is 1 over 0.5 seconds. And we end up getting 2 there. And that's 2 rotations per second, or 2 hertz. Next, we're asked to find the angular displacement. That's delta theta is our symbol for that. And during that 2-second period, the bucket makes 4 rotations. So it goes 4 times, 4 circles. Remember that each circle is 2 pi radians. So that means that makes 8 pi radians, which is about 25.1 radians as our angular velocity. The linear displacement. Well, for linear displacement, we're going to use this arrangement that delta x is equal to the radius times the angular displacement. So the radius here is going to be the length of our rope. That's 1.5 meters. Times the angular displacement, which we just established was 25.1 radians. So we do the math on that. 25.1 times 1.5. We end up with a linear displacement of 37.7 meters. Next, we want to find the angular velocity. So let's clean up top a bit here. So our angular velocity is equal to our angular displacement over time. Well, we just established that our angular displacement was 25.1 radians. And the time in which we did that was 2 seconds. So 25.1 divided by 2, we end up with 12.6. And that units on that are going to be radians per second. For the linear or tangential velocity, just remember the relationship that if we have the angular velocity and we want the linear velocity, V equals R times angular velocity. So it's going to be 1.5 meters times our angular velocity of 12.6 radians per second. Multiply that out. We end up with a linear velocity here of 18.9, and that is meters per second. Next, we're asked to find the centripetal force. We've got to remember that the centripetal force is the net force acting on an object in uniform circular motion. And you need to know the equation for centripetal force is mv squared over r. And that's just really another way of writing Newton's second law, F net equals ma. In this case, our mass is the mass of our bucket, 2 kilograms, times this is the linear velocity, so 18.9. And remember, that's 18.9 meters per second. We have to square that. Divided by the radius, which was the length of our rope, 1.5 meters. We do the math on that. We end up with a centripetal force acting here of 476 newtons. Remember, that's acting toward the center of rotation. Next, we want to find the tension in the rope when the bucket is at the top of its rotation cycle. So let's draw this out a bit here. So let's pretend that this is our center of rotation and that our bucket is, boy, that's terrible. That's a terrible circle. Let's try that again. So let's say that right now the bucket is up here. Here's the bucket. Here's our string. We want to know the tension in the rope. Now remember, the centripetal force is the net force acting on this bucket. At the top of the rotation, we have the tension in the rope, which is pulling that bucket down. We also have the weight of the bucket, which is also pulling it toward the center, which means the centripetal force at the top is going to be equal to the tension plus the weight, because they're both going in the direction of the center. That means that the tension is going to be equal to Fc minus W. Well, just a second ago, we established that the centripetal force was 476 newtons. So that's the Fc. So that's 476 newtons minus the weight. Well, the weight of the bucket is going to be the mass, 2 kilograms, times G. We're going to use 10 for G, so 2 times 10, 20 newtons. So we subtract those, and at the top, we get a tension of 456 newtons. Now at the bottom, things are a little bit different. So at the bottom, we have a tension, which is pulling toward the center, but at the bottom, we have a weight, which is going away from the center. And what that means is that our centripetal force, or if we set up an equation for centripetal force is going to be equal to the tension going toward the center minus the weight going away from the center, which means that the tension is going to be equal to Fc plus W. So down there at the bottom, the tension is going to increase. So we're going to take the centripetal force, which is 476, plus the weight, which is 20, which means at the bottom, our tension is going to be 496 newtons. All right, problem 6 deals with gravity. It says, if the distance between two objects is increased by a factor of 8, while the mass of each object is increased by a factor of 4, how is the force of gravity between the objects affected? Give a numerical answer. So we have to remember Newton's law of universal gravitation. Fg is equal to the universal gravitation times the mass of object 1 times the mass of object 2 over the distance between their centers squared. So what we're saying in this problem is that we increase that distance by a factor of 8. Well, that distance by a factor of 8, we have to square. We'll come back to that in a second. G doesn't change, it's the universal gravitation constant. We increase the mass of each object by a factor of 4. So if we compare this to what we started with, on top now we have, instead of just M1, M2 times G, we have 4 times 4 up there as well. So the top increased by a factor of 16. The bottom, we had to square that whole 8D, so that becomes 64. So the bottom increased by 64, a factor of 64. The top increased by a factor of 16. Let's reduce that down. What that tells us is that the new force is actually 1/4 of the original force. So the force of gravity between those new objects, or those two objects, is 1/4 after the change compared to before the change. So let's move on to problem 7. In problem 7, we have a satellite of mass 5.5 times 10 to the 5th kilograms. It orbits the Earth, gives us the mass of the Earth, at an orbital distance of 6 times 10 to the 6 meters. And that orbital distance is the distance between the center of the satellite and the center of the Earth. If the satellite must maintain a constant distance from the Earth, what is the satellite's orbital velocity in meters per second, and what's its period in seconds? This satellite's undergoing uniform circular motion in this problem. The centripetal force acting on the satellite is provided by the gravitation force between the Earth and the satellite. So we're going to set centripetal force equal to gravity to work this problem. Now I'm hoping that you remember that centripetal force is mv squared over r, and that the force of gravity is universal gravitation constant. And this m over here, let's back up, as the mass of the satellite. The gravitation force between the satellite and Earth would be g times the mass of the satellite times the mass of the Earth over their distances squared. Well, we're looking for the orbital speed here, orbital velocity. Before we can do that, we should notice a couple things. Mass of satellite is on both sides of this equation. It cancels out. We can also multiply both sides by r. It'll cancel over here on the left. And this r will cancel with one of those, leaving r like that. Well, that leaves us with v squared equals g times the mass of the Earth over r. So if we take the square root of both sides, that gives us v is equal to the square root of g me over r. Let's make sure that's an r, not a v. All right, if we plug in our numbers, v is equal to, well, g is 6.67 times 10 to the minus 11. And me, the mass of the Earth, we're given 5.97 times 10 to the 24th. We're going to divide that by the radius. And we're going to take the square root of that whole quantity. When we do that, we end up with a velocity of 8.15 times 10 to the third meters per second. So this thing is flying. It's going 8,150 meters per second. Way faster than the speed of sound, for example. Now we're also asked to find the period. The easiest way to do that, if you know the velocity, is remember that velocity is equal to 2 pi r over t. We're going to solve that out for t. So when we do, t is equal to 2 pi r over v. So now if we plug in some numbers, now here this t is period, not torque. So 2 pi times the radius, 6 times 10 to the 6th meters, over the velocity. The velocity was 8.15 times 10 to the third meters per second. Meters cancel. We work that out. We end up with a period of 4.62 times 10 to the third seconds. So 4,620 seconds is the time it takes for this satellite to go all the way around the Earth. All right, let's move on to problem number 8. So problem 8, a uniform meter stick is set on a fulcrum at the center of the meter stick. If a force of magnitude 2F is applied in the upward direction at the indicated point, at which labeled point must a downward force of magnitude F be applied to keep the meter stick in rotational equilibrium? A rotational equilibrium, remember that it's going to be balanced. It's not going to rotate. Remember, to get to that situation, the torque acting clockwise has to be balanced out by the torque acting counterclockwise. Well, here we're pulling up at this point. So if we pulled up over here, that wouldn't help. That would raise the board off the fulcrum. If we pulled up like that, that won't help. If we push down over here somewhere, that would cause the same kind of torque, right? Because this is causing a clockwise torque. This would be a clockwise torque. That tells us that we've got to act on this side with another force. So if we're pulling up, somewhere over here we have to pull down. Now, hopefully you remember that torque is force times length of lever arm. The torques counterclockwise and clockwise have to be equal. Well, this force is 1 unit from the center, so we could apply half a force right here, well, the distance is twice as much. So what I'm saying is 2F times 1 unit is going to be equal to, but opposite to, 1F times 2 units of distance. So those two torques are going to cancel each other out. So what that's telling us that our answer on practice problem 8 is C. The clockwise and counterclockwise torques have to be equal but opposite to each other to get into a situation of rotational equilibrium. Let's move on to problem 9. All right, so on problem 9, a disk is initially rotating around a fixed axis with an angular velocity of omega 0. At time equals 0, the two forces shown in the diagram above are exerted on the disk. So we have a 30 Newton force and a 60 Newton force. The 30 Newton force is going to try to rotate the disk in a clockwise orientation, and the 61 in a counterclockwise rotation. So the net force, 60 minus 30 newtons, is going to apply a counterclockwise torque. So there's going to be a net torque acting in the counterclockwise direction. Well, it tells us that the disk is initially rotating in the clockwise direction, and that clockwise is a negative, counterclockwise is positive. Which of the following could illustrate the angular velocity of the disk as a function of time? Well, we're starting off with a clockwise rotation. That means we have to have an initial velocity that's 0. So that rules out B, because the initial velocity right here is positive. That also rules out D, which has it looks like a 0 initial velocity. So neither one of those work. So that leaves us with either A or C. Both start with an initial velocity that's negative. Well, this has a net torque in the positive direction, which means we're going to get acceleration. Remember that in a velocity time graph, doesn't matter if we're talking about linear velocity or angular velocity, the velocity of the slope of a velocity time graph is equal to acceleration. We're going to get an acceleration in the positive direction this time, and it's going to be a constant positive acceleration, which means that A is our answer here. Notice that C shows there's a constant positive acceleration for a while, but then there's a negative acceleration. In this particular situation up here, there's nothing there that would cause that negative acceleration. So it looks like A must be correct. We start with a negative angular velocity. We end up with a positive angular acceleration, and that pattern seems to be consistent with all our possible choices. So for problem 9, answer A. Let's move on to problem 10. So in this case, we have a merry-go-round. We have our rider sitting there at the center. We're looking down on it. The rider has a mass of m. The merry-go-round has a mass of 4m, rotating in a clockwise direction. Assume that the platform rotates with 0 friction. Which of the following describes an action of the rider that will increase the angular momentum of the rider merry-go-round system? Well, now we're assuming there's no external forces acting. The rider's just sitting on the merry-go-round or moving possibly on the merry-go-round. Remember that angular momentum is one of those quantities that's conserved. We use the symbol L for angular momentum. It's a conserved quantity. And what that means, as long as there's no net forces or net torques acting on the system, that angular momentum stays the same. So it doesn't matter if the rider moves toward the center, or moves away from the center, or moves in the opposite direction of the merry-go-round's rotation. None of those is going to change the angular momentum of the system. They may speed up or slow down the merry-go-round, but it's not going to change the total momentum of the rider merry-go-round system. So our answer here is D. Let's move on to number 11. Now 11 looks like the same problem, and it sort of is. But this is which of the following describes an action of the rider that will increase the angular velocity of the merry-go-round system. So now we're just talking about the velocity of the merry-go-round, rather. Well, here's the thing. We know that angular velocity, or angular momentum rather, is equal to the moment of inertia times the angular velocity. Remember that moments of inertia are going to be equal to maybe some fraction times mr squared. Mass times the distance from the center of rotation squared. So anything that will make this r bigger is going to increase I. Anything that's going to make r smaller is going to decrease I. Well, here's the thing. Let's set up an equation for when the rider's where he's at. So we're going to say that the angular momentum, which is conserved, is equal to the angular momentum. So we'll say angular momentum before equals angular momentum after. Well, let's say the angular momentum before is I times omega. If that rider does something to decrease I, then the angular velocity has to increase, because these two quantities times each other always has to be equal to these two quantities equal to each other. What that tells me is that our answer on problem 11 is A. Because as the rider moves toward the center, that decreases R. Well, when R decreases, I gets smaller. And if the moment of inertia gets smaller, to conserve angular momentum, the angular velocity has to increase. So A looks like a good answer. If you've ever tried this on a merry-go-round, it works. If you start out far on the edge of the merry-go-round and you move toward the center, the merry-go-round will speed up. It's the same idea that causes a figure skater to spin faster when she tucks in her arms. Let's move on to problem 12. All right, on practice problem 12. The wheel on a car has a rotational inertia of 4. At the moment that the wheel has a counterclockwise angular velocity of 8 radians per second, an average counterclockwise torque of 4 Newton meters is applied for 4 seconds. What is the angular velocity of the wheel at t equals 4 seconds? So the wheel is spinning in a counterclockwise direction. It's spinning in a counterclockwise direction at 8 radians per second. And now we're applying a torque. That torque is going to cause an acceleration. So to work out this problem, you have to realize that the torque is equal to the moment of inertia times the angular velocity. This is sort of the rotational equivalent of Newton's second law. F net equals ma. And I wrote this wrong. This should be an alpha. So that's rotational inertia times angular acceleration. We're going to solve this out for alpha. So alpha is equal to the torque over the rotational inertia. Plug in what we know. So alpha is equal to the torque, which is 4 Newton meters, divided by the rotational inertia, which is 4 kilogram meters squared. Well, that ends up giving us an alpha of 1, and that's 1 radian per second squared. That's our angular acceleration. What we're trying to find is the final angular velocity. Well, remember that we have rotational equivalents of all our kinematic equations. If we were doing a linear kind of problem and we were trying to find a final velocity, we would probably use V equals VO plus AT. Well, we have a rotational equivalent. Looks like this. Final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. So to work this out, our initial angular acceleration was 8 radians per second, and that's in the counterclockwise direction, so that's the positive direction. plus the angular acceleration of 1 times the time. Well, this goes on for 4 seconds. So notice that second is going to cancel out one of those. So that's going to give us 8 radians per second plus 4 radians per second. Our final angular velocity is going to be 12 radians per second. And that is answer D on problem 12. So let's move on to problem 13. All right, so on problem 13, this looks like the same problem we just worked. But this time, same situations, it's asking for what's the change in angular momentum. Well, remember that angular momentum is equal to the moment of inertia times the angular velocity. So let's calculate the initial angular momentum. Well, that's going to be equal to the I, the moment of inertia, 4, times the initial velocity, angular velocity, and that was 8. So that means the initial angular momentum is equal to 32. All right, we found in the previous problem that the final angular velocity was 12 radians per second. Well, that means that the final angular momentum is also equal to I times angular velocity. So the final angular velocity is going to be 4 times the new velocity, 12. That means that the final angular momentum is equal to 48. Well, this asks for the change in angular momentum. We started with 32. We ended with 48. That means the angular momentum changed by a factor of by 16. So answer A is our correct answer on problem 13. Problem 14. A system consists of 2 balls of clay of mass m and 4m connected by a bar of negligible mass. The rod is held by a child at the system's center of mass with the rod in a horizontal position. The rod is then released from rest near the surface of the earth. Which of the following explains why the system does not rotate around the center of mass as it falls? So this is what our system looks like. What we're saying, if someone holds this at the center of mass and drops it, it's just going to fall straight down. It's not going to begin to spin. And you can look through the choices here, but it looks like the best choice, the correct answer here, is B. So this says the Earth exerts a larger gravitational force on the sphere of mass 4m. That's true. So there's going to be more gravitational force between this and the Earth than there is between this and the Earth. But the larger sphere is closer to the system's center of mass. In this situation, the center of mass is always going to be closer to the bigger part of the mass, maybe something over here. That's true. Than the smaller sphere. This leads to a condition in which there's no net torque. So we're saying that the torque over here is going to be equal to the torque over here. And if that's true, this system is going to be in rotational inertia and it won't rotate. So it looks like answer B is the correct answer on problem 14. Let's move on to problem 15. All right, so the Earth moves in an elliptical orbit around the sun. The mass of the Earth is much less than the mass of the sun. At the instant illustrated in the diagram above, the Earth is moving away from the sun. How does this affect the magnitude of the angular momentum of the Earth with respect to the sun? We've got to remember that as a planet moves away from the sun, that its angular velocity is going to decrease. So the force of gravity acting on it is becoming a little bit less. But as it moves away, its moment of inertia is going to increase. And it turns out the changes in those two things are proportional to each other. So the net effect is, as it moves away, the angular momentum of the Earth doesn't change. So answer C is what we're looking for here. Yes, the velocity does slow down, but I increases, and it's a wash. So the answer here is C. This has no effect on the angular momentum of the Earth. So now let's move on and look at problem 16. Same basic kind of question. This time we want to know, how does moving away, how does it affect the potential energy of the Earth-Sun system? Well, in this case, we need to think about the problem. When two objects are far away, the potential energy between them, we can calculate using this equation. So as an object moves away from the sun, it actually gains potential energy. So our answer here is A. And the reason that's true is that as they move away from each other, we're going to think of R as a negative value, moving away. So this R is going to become negative. Well, now we're going to have a negative over a negative, which means that the change in potential energy is going to become a positive number. So answer A, as the Earth moves away from the sun, the system is going to gain potential energy. So now let's look at problem 17. The figure below illustrates a door hinged on its left side. So the hinges of all these doors are over here. Assume that there is negligible friction at the hinges. The arrows indicate forces of different magnitudes applied to the door at different locations. In which situation will the angular speed of the door increase at the fastest rate? Well, the angular speed is going to increase the most when alpha is the greatest, the angular acceleration. Well, the angular acceleration is going to be the greatest when the net torque acting on that object is the greatest. Well, we know that torque is equal to force times length of lever arm. So we want to know, when is this relationship the greatest? So if you look, here we have a force, but it's really close to the hinges. So F, and we're going to have a really little R. In B, we have twice the force, but the same R. So the torque here is going to be bigger than the torque here. In C, we have the biggest force, and we have the greatest distance from the hinges. So this looks promising. In D, we have a force of magnitude F at the same distance as the force in C. But if we compare C and D, they have the same R, but C has a much greater force, which means it's going to have a much greater torque. So because the force and the radius multiplied together give us the greatest torque, our answer here is C. That great torque is going to lead to a large angular acceleration, which will cause a faster increase in the speed of the door. So answer C looks good on problem 17. All right, so on problem 18, a fulcrum is placed at the center of mass of a uniform meter stick. So the fulcrum's at the center of mass, that's important. A mass is placed on top of the meter stick to the left of the fulcrum, and we see that mass right here. A child is asked to place a second mass with less mass than the original mass on the meter stick so that it will balance out horizontally. Which of the following quantities are needed to determine where the second mass should be placed? Well, we know since the second mass is less than the first mass, it's got to be placed further from the center of rotation, further from the fulcrum. So it's going to have to be out here somewhere, because we know that the torque on the left has to be equal but opposite to the torque on the right. And we know that torque is Fr times Fr. And in this case, the forces are going to be the weights. So it could be mg times r has to equal mg times r. We don't know either mass. We also don't know either r, either distance from the fulcrum. According to this equation, those are the two things that we need to know. This is one of those questions where you have to pick two answers. What we need to know to determine where to put that second mass is we need to know the mass of both masses. That'll take care of this m and this m. And we also need to know the distance to the fulcrum from this first mass, r. And if we know those, the only unknown variable will be the distance between the second mass and the fulcrum. So that's the other thing that we need to know. So our answer on problem 18, A and also D. All right, so in problem 19, we have a system which consists of a merry-go-round rotating on a frictionless axle. And notice that merry-go-round is It's rotating in a counterclockwise direction with a linear speed of v, and we have a child running toward it at a speed of v over 4. And notice the child is running in a clockwise direction. The child hops on the merry-go-round, and we're specifically told to ignore any torques or forces that may have occurred as the child pushed off the ground. How does the angular momentum of the system, now remember the system is the child and the merry-go-round, change after the child gets on the merry-go-round? Compare the angular momentum of the system before the child gets on. And this should say compared to, should be a D there. So here's the thing. The system is the child and the merry-go-round. We've talked about before how that angular momentum is a conserved quantity, that the initial angular momentum is equal to the final angular momentum of the system. And that's always true unless there's an external torque acting on the system. Well, this problem pretty much tells us that's not true. So our answer in this problem is D. It's the same because there's no external torques in this case acting on the system. So now let's move on to problem 20. Two robots sit on a rotating turntable that is spinning in the counterclockwise direction. Assume that there is no friction in the bearings of the axle. How does the angular speed of robot A compare to the angular speed of robot B? Well, remember that angular speed is equal to change in angular displacement over time. What you've got to realize about object A and B is that every time one of them makes a circle, so does the other. That means that the angular displacement is the same regardless for A and for B. The time is the same, which means that their angular velocities are the same. So our answer here, C. They have exactly the same angular velocity. So let's move on to 21. 21, same kind of problem, except this time we're asking not about the angular velocity, but we're asking about the linear speed. Now what you've got to realize here is that linear speed is equal to r times angular velocity. And notice that B is located further from the center of rotation than A. So that means that r for B is greater than it is for A. And therefore, since B's radius is larger than A's radius, B is going to have a faster velocity than A. Well, the question asks about the speed of A compared to B. That means that A, since it has the smaller radius, is going to be going slower. So our answer here, because it has a smaller radius, because it's located nearer to the center of rotation, robot A is going to be traveling with a lower linear speed, even though the angular velocities are the same. Problem 22. We're referring to problems 20 and 21. Robot A begins to walk in a circular path in the opposite direction of the turntable's rotation. How is the magnitude of the angular momentum of the turntable alone, not the system, affected? All right, so on problem 22. Robot A begins to walk in a circular path in the opposite direction of the turntable's rotation. How is the magnitude of the angular momentum of the turntable alone, not the system, affected? So our turntable is rotating in a counterclockwise direction. So robot A begins to walk in a clockwise direction. To go that way, he has to push off with his feet against the turntable in the counterclockwise direction so that the turntable will push him in the clockwise direction. So he's applying, robot A counterclockwise torque. Well, since there's a counterclockwise torque acting on the turntable is going to have a counterclockwise angular acceleration, which means there's a net counterclockwise torque, there's a counterclockwise acceleration, which means the velocity of that turntable is going to increase. Remember that angular momentum is equal to moment of inertia times angular velocity. Well, since the angular velocity is going to increase, the angular momentum of the turntable is also going to increase. So answer A is correct. Now, the angular momentum of the system is not going to change. But in this case, that's not what we're asking about. We're asking about the angular momentum of the turntable alone. The turntable is going to speed up in the counterclockwise direction as the robot speeds up in the clockwise direction. So problem 23. Problem 23. It says a planet has 3 times the mass of Earth and 5 times Earth's radius. The magnitude of the gravitational field near the planet's surface is. When we're looking for the gravitational field, we're going to set the weight of an object on that planet's surface equal to the force of gravity between the object and the planet. Remember that weight is equal to mg, and this is the mass of the object. We'll just use O times g. And the force of gravity between 2 objects is equal to the universal gravitation constant, mass of the object, mass of the planet, over r squared. Well, notice the mass of the object is on both sides of the equation, so it'll cancel out. So we end up with g, little g, equals gravitational constant, mass of planet, over r squared. This little g is the gravitational field strength, or the acceleration due to gravity. So this is the equation we're going to work from. So in this particular problem, the new planet has 3 times the mass of the Earth. So if we set up a new equation down here, the mass of the planet is 3 times the mass of the Earth, and it has a radius that's 5 times. So we're going to take 5 times r, and we're going to square that. Well, what that means is this. That means the new gravitational field strength is increased by a factor of 3 when we increase the mass of the planet, and that it's going to be decreased by 5 squared, or 25, when the radius increases. So the new gravitational field strength is 3/25 of the field strength of Earth. Well, notice that's not one of our answers. Well, what you do know, though, is that the field strength of Earth is equal to 10 newtons per kilogram. That's the gravitational field strength of Earth. The gravitational field strength on this particular planet is 3/25 of that. So if we take 3/25 of 10, we end up with 6/5 newtons per kilogram. There should be a G here, newtons per kilogram. So our answer is B. All right, so let's move on to problem 24. 2 pieces of space junk of equal masses are in circular orbits around the Earth. Object A has a speed of v. The orbital radius of object B is 16 times that of object A. What is the speed of object B? All right, here's what you got to think about. Remember that when 2 objects are in orbit, we're going to set their centripetal force, or net force, equal to the force of gravity acting on them. Remember that centripetal force is mv squared over r. This is the mass of, in this case, we'll just use a J for the junk. And that's equal to the gravitational force, which is G, times the mass of the piece of junk, times the mass of the planet, in this case Earth, over r squared. Notice the mass of the junk cancels out. One of these r's is going to cancel out that square. So we end up with v is equal to the square root of G, mass of the planet, over r. So here's the thing. This new planet is going to have a radius that is 16 times that of object A. So object B's radius is going to be 16 times object A's radius. Well, when we take the square root of that 16, after we take the square root, becomes 4. So that means that the new velocity is going to be 1/4 of the original velocity, or if, in this case, the velocity of object B is going to be 1/4 the velocity of object A. We could think of it this way, is that the velocity is proportional to the square root of 1 over r. All right, so it looks like our answer here, object D, the velocity of object B is going to be 1/4 the velocity of object A because it is 16 times further away from the Earth. Problem 25. A satellite orbits a planet in a circular orbit. The mass of the satellite and the distance between the center of the satellite and the center of the planet are known. What additional information is needed to calculate the speed of the satellite? Well, in the previous problem, we derived this equation where the orbital speed of a satellite is equal to the gravitational constant, universal gravitational constant, times the mass of the planet or sun, whatever we're dealing with, over the orbital distance or orbital radius. That's an R, not a W. So if we look at what we need, in this case, we know the mass of the satellite. We don't really need to know that anyway. We know the distance between the satellite and the center of the planet. That's R. G is the universal gravitation constant. We know that. So the only other piece of information that we need to know to calculate this orbital speed is the mass of the planet, which in this case is answer C. So let's move on to problem 26. A person who weighs 1,250 newtons on Earth travels to another planet that has 3 times the mass of Earth and 4 times the radius of Earth. What is the person's weight on that other planet? Well, let's think of it this way, that the weight is caused by the force of gravity between the person and the planet. We know that the force of gravity is G times mass, we'll say mass of person, times mass of Earth over r squared. So now, on the new planet, the mass of the planet is 3 times. We're going to assume the mass of the person doesn't change. This new planet has 3 times the mass of Earth, and its radius is 4 times larger. Well, this 4, we've got a square. Well, what that tells me is that the weight of this person on this new planet is going to be 3/16 of his weight on Earth. So we need to take 3/16 of 1,250. And when we get 3/16 of 1,250, we end up with an answer of B, 234 newtons. So that's problem 26. Let's move on to problem 27. A student whirls a ball on a string of radius r in a horizontal circle. The ball undergoes uniform circular motion, which you guys should know by now means that it's moving at a constant speed, but that it's constantly accelerating toward the center of rotation. Which of the following best illustrates the direction of the velocity of the ball at point X? So this ball is going to rotate counterclockwise when it gets here. What I'm hoping that you realize is that at this point, there's going to be a centripetal force pulling that ball toward the center. There's going to be a centripetal acceleration toward the center. The velocity, the linear velocity of an object is always perpendicular to the centripetal force and the centripetal acceleration, which means our answer here is going to be C. And we know it's going in this direction because of the counterclockwise rotation. Some of you might be tempted to put B. Because it's rotating this way, if the string broke when this ball got to point X, it would move off in a straight line to the right. So C looks correct for problem 27. Problem 28 looks like the same problem, but this time we want to know which best illustrates the direction of the net force acting on the ball at point X. So again, that ball is going to rotate around. At point X, there's going to be a centripetal force acting on it. There's going to be a centripetal acceleration acting on it, and it's going to have a linear velocity. The centripetal force and the centripetal acceleration, when an object is in uniform circular motion, always acts toward the center. So that means our answer is going to be A. It's the one pointing toward the center of rotation. Problem 29, again, looks like the same problem, but this time we're looking for the direction of the acceleration. And as I told you a second ago, the centripetal acceleration is always going to be toward the center. It's always going to act in the same direction as the net force or the centripetal force. So on 29, the answer is also going to be A. Finally, problem 30, two bags contain an equal number of identical masses. The two bags are separated by a distance r. 1/3 of the apples from one bag are moved to the other bag. If the magnitude of the original gravitational force between the two bags was F before moving the masses, what is the magnitude of the gravitational force after the masses are transferred? So we have these two bags. And let's say they have apples in them. They start off being equal. So the force of gravity between those two bags would be equal to G times first mass times second mass over r squared. Then we move 1/3 of the apples from one bag to the other bag. Let's say we're moving them this way. So now the new force is going to look like this. This original bag lost 1/3 of its apples. So now instead of having a mass of M1, it's going to have a mass of 2/3. In this other bag over here, it gained 1/3. So it had 1 plus 1/3. Its new mass is going to be 4/3 of that original mass. We didn't mess with the radius, it's the same, which tells me that the new force is equal to 2/3 times 4/3 of the original force. The new force is 8/9 of the original force. So answer D is the correct answer on problem 30.